Yes. Firstly, let me recall some definitions. Let G be a graph and let lambda be an eigenvalue of G. A real valued function f defined on the vertex set of G is called a lambda eigenfunction of G if it has at least one non-zero value and the equality lambda f of x is equal to the sum of values of f on all neighbors of x holds for any vertex x. And the subpart of a function f is a set of its non-zeros. Okay, now we consider problem 1. Let G be a graph and let lambda be an eigenvalue of G. The problem is to find the minimum cardinality of the support of a lambda eigenfunction of G. This problem is known as the minimum support problem or simply the mass problem. This problem is closely related to the intersection problem of two combinatorial objects and to the problem of finding the minimum size of combinatorial trace and null designs. Okay, now let me briefly discuss some results on the mass problem. The minimum support problem is studied for various families of distance regular graphs and Cayley graph on the symmetric group. For example, this problem is studied for the Hamming, Johnson, and Grassmann and Doom graph, for the bilinear form graphs, for Paley and generalized Paley graph, and for the star graphs. Let me recall the definition of the Hamming graph. Sorry, let sigma q be q-let alphabet. The Hamming graph with parameters n and q is defined as follows. The vertices of this graph are all words of length n of alphabet sigma q, and two vertices are adjacent if they differ in exactly one coordinate. The Hamming graph H n2 is also known as n-dimensional hypercube or n-cube. The Hamming graph H and Q has n plus 1 distant eigenvalues, lambda I of nq of this form, and denoted by ui of nq, the lambda I eigenspace of the Hamming graph. The direct sum of subspace ui, ui plus 1, and so on, uj is denoted by uij of nq, and the set of all real valued functions defined on the vertex set of the Hamming graph is denoted by u of nq. Now we consider two generalization of the mass problem for the Hamming graph. Denote mij of nq is equal to the minimum of the support size of a function f, such that f belongs to the space uij and f has at least one zero value. And a function f from the space uij is called optimal in this space if its support size is equal to mij of nq. So problem 2 is to find mij NQ, and problem 3 is characterize functions that are optimal in the space Uij of NQ. Now we briefly discuss results on these two problems. Problem 2 is completely solved for all n and q, and problem 3 is solved for q is greater than or equal 3, and I, well, j is less than or equal n, and the second case. And so you can see that problem 3 is open for the following two cases, and in this talk we will consider the first case when q equals 2. So we will consider problem 3 for the hypercube. Let me recall the lower bound for this case. In this case, we have the following theorem. Let f belongs to the space Uij, and I plus j is greater than or equal to n, and if and f has at least one non-zero value, then the supersize of f is greater than or equal to 2 in the power I. And in the second case, we have that the supersize of f is greater than or equal to 2 in the power n minus j. These bounds are sharp, and optimal functions achieving these bounds can be constructed as the tensor products of several elementary optimal functions. Now we define three types of elementary functions. We define a function phi k and psi k on the vertices of the k-dimensional hypercube as follows. Phi k of x is equal to 1 if x is a all zero vector, f k of x is equal minus 1 if x is a all ones vector, f and is equal 0 otherwise, and function psi k of x is equal 1 if x is a all zero vector, is equal 1 if x is a all ones vector, and is equal 0 otherwise. So these two functions, phi k and psi k, has support size 2, and we define a function ik on the vertices of the hypercube as follows. Ik of x is equal 1 if x is all zeros vector and is equal 0 otherwise. And you can see the function phi3, psi3, and i3 on the slide. The first two function has support size 2, and the third function has support size 1. And okay, now we define one type of the equivalence of functions. Two functions f and g defined on the vertex sets of the hypercube are called equivalent if there exists an orthomorphism phi of the hypercube and a real non-zero constant c such that g of x is equal to the c times f of pi of x for any vertex of the hypercube. Okay. Now we discuss the main results of the talk. The first result is theorem 2. Let F belongs to the space Uij and 2, and I plus j is greater than or equal to n. Then the support size of F is 2 in the power of I, if and only if F is equivalent to the following tensor product. In these tensor products, we have I functions of the first type and 1 or 0 function of the third type. And we have that numbers n1 and so on and k are all positive integers, numbers m1 and so on, and are even positive integers, and k and r are negative integers, and k plus l is equal I, and l is greater than or equal n minus j, and know that the cases when k is 0 or l is 0 or I is 0 is possible, are possible. And so if we have a partition satisfying the conditions of theorem 2, then this partition gives optimal function, gives functions that optimal in space Uij. And if you consider the case when I equals j, we have only one partition satisfying theorem 2. In this case, we have the following result: let F belongs to the space Ui of n, and I is greater than or equal n over 2. Then the supersize of F is 2 in the power I, if and only if F is equivalent to the following tensor product. So for eigenfunction, we have only one optimal eigenfunction up to equivalence. But for general case, the number of optimal functions is not one. It may be 2, 3, and so on. And sorry, let me consider one small example for theorem 2. Let n equals 4, I equals 2, and j equals 3. Then in this case, there are exactly two partitions of 4 such that k plus l equals 2 and is greater than or equal 1. We have partition 4 is equal 2 plus 2, and 4 equals 1 plus 2 plus 1. And these partitions correspond to the optimal function phi2 times phi2 and phi1 times phi2 times phi1 respectively. And now we consider the second case. In this case, I plus j is less than or equal n, and we have that the supersize of f is equal to 2 in the power n minus j, if and only if f is equivalent to the following tensor product. This product contains three types of functions: psi, phi, and I, and we also have some special conditions on the partitions. In this case, we have k plus L equals n minus j, and L is greater than or equal I. And as for theorem 2, in this case, if we consider I plus j, we have the following result. So in this case, any optimal eigenfunction is equivalent to the following tensor product. And okay, and finally, we discuss the properties of the spectrum of optimal functions. Let me recall some definitions. Any function f from the space UN2 can be uniquely represented as the following sum. In this sum function, the function fi is the projection of f into eigenspace ui, and the spectrum of a function f is the set of numbers I such that the corresponding function fi isn't identically zero function. And okay, so using theorems 2 and 3, it isn't difficult to obtain that the spectrum of optimal function forms an arithmetic progression with common difference 1 or 2, and more precisely, we have the following result. Let f belongs to the space uij of n, and I plus j is greater than or equal n. If the support size of f is 2 in the power I, then the spectrum of f is the arithmetic progression I plus d, and so on, I plus kd, where the first term of this progression is I, the common difference d is 1 or 2, and k is non-negative integer, and I plus kd is less than or equal j. And note that the case when k is 0 is possible, and in this case, the spectrum of f is consists of only one number I, and this case corresponds to the eigenfunctions. And the second case, in the second case, we have that the spectrum of f is a projection, is an arithmetic progression j minus kd, j minus k minus I d, and so on j, such that d is 1 or 2, k is non-negative integer, and j minus kd is greater than or equal I, and in this case, the case when k is equal to 0 is possible too, and in this case, the spectrum of f is equal to j. If you consider a function defined on the vertex sets of the hypercube, and if you know the spectrum of this function, then we can use these results to prove that this function isn't optimal. For example, suppose f belongs to the space U at J, and the spectrum f is not an arithmetic progression of a special kind, then this function is not optimal. For example, if we consider the case when f belongs to the space UN2 and the spectrum of f is equal 0, 3, then by previous results we have that this function is not optimal, so the supersize of f is greater than 2 in the power of n-3. Okay, that's all. Thank you very much.